Okay, hot take. I'm excited to show you something. Let's show how a quantum computer is going to work. But let's start out by, by looking at some fundamentals. What we're trying to do is represent a quantum state. We're going to use an oscillator to do that. Oscillators are widely available, where they're pretty well engineered. We know quite a lot about them, and they involve the analog engineering, the analog side of engineering. So the equation of a photon we have is this C equals lambda times nu. Okay. And we also have this constraint, if you want to call it, such that C is equal to 1 over this square root of this electrical and magnetic permittivity. And we also have this constraint that says that nu, or it's not a constraint, it's just a relationship, this 2 pi times frequency, right? And this is like hertz frequency. Now, for those of you who are, the implementation, if you want to call it that, right? You might have something, you might notice that this looks very similar to 2 pi over LC. A lot of oscillators are based on this design. So it gives you an intuitive sense between these two quantities. Okay. We're going to create a single complex number from an oscillator. So here's our integer. In classical computing, in digital computing, we had an integer. In quantum computing, we still have an integer. So here's your integer. Your integer is like an oscillation. It's a revolution. That oscillation, this ball is going to start here and then go this way. And then it's going to reach here. But really, we're looking at the projection down here, right? And then when it's here, and so on. So really the motion we're interested in is this one. Nonetheless, we have this ball going around in a circle conceptually. It starts at at 1, and then it goes all the way until it's 0 in the real axis, but then there's an imaginary component. And then it goes all the way until it's -1 in the real axis, but the imaginary is 0, and then all of a sudden we have a negative imaginary, but we have it being at 0. So really the oscillator is like a sine wave. In this sine wave, we have this moment where there's 0. Right here is 1. Right here is 0 again. Down here is -1. Here, somewhere around here is 0 again. Somewhere around here is 1. Again, somewhere around here is 0. And somewhere down here is -1. Again, somewhere here is 0. And so on. I think in textbooks, they might say something like the quantum state is equal to, alpha times 0 plus alpha 1 times 1 or something like that. Okay, So let's keep going. Okay, so we look at that picture again, but here in a higher dimension. So we're going to take, we're going to create, remember we created a first, and now we have the second. That's this one here, second. And this one is just like the first. We're going to have some ball going around in a circle. Again, we have the state here of 1, we have the -1 here, and then we have this 0 state here. Now, because we have, right, we're going to have this imaginary part and then a negative imaginary part again. We're going to have that again, but we need new terminology because we've used, so we're going to use -I and +I, we still have the imaginary terminology, and then we still have the real, right, the number, the states, like 1 or -1. What we're going to do is we're going to use like a bit of a phase, call it a phase, and that's this, or no, you know what, direction maybe, like of travel. Here, it's all of these things. In some ways it's a phase, in some ways it's a direction of travel, and in some ways it's like a sense direction or a polarity. Like, allow it to be all these things for a second. We're not going to say it's one thing. It's going to be helpful. That's what it is. It's helpful. Helpful. Who cares? That's what it is. And you're going to use it as a creative tool. So just keep that in mind. It's helpful. It's this phase direction or sense direction. Okay, let's see here. So we have two complex values. One is one ring, and the other is another ring. And they all, both rings intersect at exactly one place, which is, that state, if it's that. And if it's this. So in this picture, you kind of have that lambda is this part. And then you have nu is that part. So, okay, here's another picture of a single state. Notice the 0 state is in the middle. And another picture, just kind of going for visualization. This is my practice. And then we have a quantum state. Okay, so in here we start with this fundamental equation, but we want to visualize it. So here's how intuitively we'd write it. We'd say 0, 1, all the way to the nth component is, we'd do some normalization, but then we'd come out with this state vector that looks like this. And we can visualize those states. All of them here are at the top, right? So we have this, and we have the green state, the red state, and then we have this purple state. Here they are written in a matrix form, if you can imagine. It's like a trace, right? This matrix is some signature, right? This is some signature of light. Signature. Okay. There's more to talk about, but I think that's a good start. If you can grasp this part, then you're well suited to wave-based computing. Thank you for taking a moment to just listen in, give me some practice here. Tune in soon. Thank you. Bye.